standing waves and resonance, and then we will move to Doppler effect. So waves with the same amplitude and wavelength traveling in the opposite direction create an interference. Remember what we said yesterday about the interference? And the interference is how the waves are. So the interference is when the waves are interacting between each other. So when we see that two waves are meeting together at a certain point, then what may happen during the interference is that is known as a constructive interference or deconstructive interference. Now, same waves, not same amplitude and wavelength waves are traveling in the opposite direction. So as you see here, we have wave A that is represented by those dotted lines, and wave B that is represented by this continual line here. And when they are meeting together, what is happening is that the waves will be cancelled out. And when they meet where the maximum and minimum of the waves is, this is called nodes. Okay, so nodes of the wave. So as you see it here, those are the nodes. The resultant displacement of those two standing waves is like cancel out, is nothing exists there. But if we have two waves that do not have the same amplitude, so wave A is again represented by this dotted line here, and wave B that is continuous line, and they are moving into opposite direction. What is happening is that they, when they meet together, the resultant will be adding those two together. Okay, so what do you see as the resulting wave here is a line that goes where we are adding all of those two amplitudes together. Okay. The best observation for standing or stationary waves is when a string or a wire is fixed in both ends. And then what do? Is you just create a vibration, and then you see that what is happening on that case. The frequency at which the standing wave can exist in the string is given the length is by the natural length of the string. Okay. So now when you just create a vibration in a string that has both ends are fixed, then what do you see is that the wave will move, or the string will move on as you see it here. But one complete, again, the same principle that we did, one complete or evolution of the whole wave will give us what is the wavelength. Okay, and then as you see it here, we are giving this motion, and then the displacement of every point in the string is going to be either going down or heading up, depending on what is happening with the wave or the particle on that point. So when we have a string that is with both ends are fixed, like fixed point A and point B is a fixed one. And an example of this is a guitar string, let's say, or a violin string. So then what is happening is you are vibrating it, and then the string will vibrate as a whole. So see, it's going up and going down. Standing wave for 5 resonance frequencies are those ones here that you kind of have to remember them. When we have the first harmonic, or n is equal 1, then what we see is one loop. And when we say one loop, is that it goes from this direction to this direction. Okay, so it's completing one kind of full loop, but in 2 different ways. And when we have the second harmonic, then we have two loops like this. Third harmonic, we have 3 loops. Fourth harmonic, we have 4 loops. 5 harmonic, we have 5 loops. And the way that we calculate the wavelength is lambda is equal to 2L over n. And then the frequency is based on the universal equation of the waves. V is equal F times V over lambda. Now, as you see here, if we have, and this formula is kind of self-explanatory. It's 2L because it is going in both sides, and then over 1 because it is only one harmonic, and then or one arc that you see, one time that you see this arc here in the length L, and then second harmonic because you see 2 arcs here, third harmonic because you see 3 arcs, and so on. And the formula is kind of given because it is like it goes in both sides, since it is in both sides is fixed, and then it traveled twice this length. And then you see the frequency, or the wavelength is equal to 2L over n. For standing wave patterns that exist, the number of wavelengths on the string depends on the L of the string. And for the first harmonic, we have half of the wavelength, has to be half of the wavelength. For the second harmonic, it has to be 2, and so on. The general equation is, as we said it even before, is lambda is equal to 2L over n. Lambda is equal to 2L over n, where n is equal to 1, 2, and 3. Now, if we have an example here, what is the wavelength of the fourth harmonic on a string of 2.4 meters? So now we are assuming here that the string is in both ends is fixed. So the wavelength will be 2L over n. Now we know what L is as 2.4, and we know what n is as its fourth harmonic. So this will be 2 times 2.4 meters over 4, and this will be 1.2 meters. So this is telling us that the wavelength of this particular string is 1.2 meter. Again, keep in mind what the wavelength is. So if you have a wave that goes like this, the distance between the 2 maximum or 2 minimum or 2 same nature points on the wave will be the distance or the wavelength of the string. So now another example is a third harmonic standing wave appears on 1.80 meter strings when the frequency is this. What is the speed of the wave on the string? Okay, on this case, what do you think that the approach needs to be? How can we approach this kind of question? The length of this is 1.80 meters. We know that the frequency is 32 hertz. Yes, correct, Nicole. And what do we know is that we are dealing with third harmonic. So n is equal to 3. Now, since we have a string that is tied into, two ends are fixed, then the wavelength will be calculated as 2L over n, or 2 times 1.80 over 3. And this will be, okay, so this is 1.2 meters. Now that we have the wavelength and we have the frequency, we can find the speed as f times lambda. So this will be 32 times 1.2 meters, and this will end up to being meters per second. And the result here will be, what is it? So now let's see the resonance in air columns. So if we have an air column, then what is happening, it's it's called, first of all, it's called a closed air column because you see it here, it's kind of one side is closed and the other one is open. Then the resonance will occur when we have 1/4 lambda or 3/4 lambda, 5/4. So with an increment of 1/4. So 2L times 1/4. But so as you see it here on the first one is at 1/4, and then it moves to 3/4, and then 5/4, 7/4, and 9/4, and so on. What do you see when you have 1/4 length? It's that you see half of the wavelength, half of the wave. And then when you have 3/4 lambda, then you will see this one here, 1, 2, and then this is half. Okay. There are open air columns. When there are open air columns, then you will see at 1/2, 2/2, which is 1 lambda, and then 3/2, and so on. So when it is closed, the increments are 1/4, 3/4, 5/4, and so on. And when it is open column, then it is 1/2 in increments of 1/2, 2/2, 3/2, and so on. The equation that relates, this is again something that you need to remember. The equation that relates the resonant length with the wavelength for the closed air column will be 2n minus 1/4 times lambda, where n is equal 1, 2, 3, 4. And for open air is n lambda over 2, where n is equal to 1, 2, 3. So this again proves that when n is equal to 1, 2 times n over 4 is 1/4 lambda, and then 3/4 lambda, 5/4 lambda, and so on. And this will be 1/2 lambda, 2/2 lambda, which is lambda, and then 3/2 lambda, and so on. Okay, let's see this example here. The first resonant length of a closed air column occurs when the length is 18 centimeters. So length is 18. This is an example. 18 centimeters. What is the wavelength? What is the wavelength of the sound? And if the frequency for B is, if the frequency is 512 hertz, what is the speed of the sound in air? How will you approach this kind of question? As we mentioned here, is L is equal to 2n-1 lambda over 4. So now on this formula, what do we know is that the L is 18 and we are looking for lambda. In our case, so this will be lambda over 4 because n is equal to 1. So then from here we find that lambda is equal to 4 times L, or 4 times 18 centimeters, which will be equals to, that is 4 times. And then for B, what we will do, since the frequency is given 512, what is the speed? We will use the universal equation of the wave. So V is equal to F times lambda. We know what lambda is. We know what frequency is now. So it will be 512 hertz times 72 times 10 to the power of -2 meters. And the results will be meters per second. And then the frequency will be 368.664 meters per second. You can easily say 367 meters per second. And this is pretty much what the speed of the sound, the voice is. Okay, do you have any questions? Okay, so this is another example. An organ pipe with a length of 3.6 meters long, open at both ends. So now we are dealing with an open air column, produces a note at the fundamental frequency. What is the wavelength of the note produces? And if the speed of the sound is 346 meters per second, what is the frequency of the pipe? So what we have here, L is 3.6 meters, and we are looking on A for the wavelength and on B for the frequency. Frequency, knowing that the speed is 346 meters per second. Okay, so how are we going to start on this case? So using the fact that this is an open air, open end air column, then will be n lambda over 2. Since n is equal to 1, then lambda L is equal to lambda over 2, which gives us that lambda is equal to 2 times L, or 2 times 3.60 meters, and this will be 7.2 meters. So this is the wavelength of this particular sound. And now we know that the speed of sound is 346 meters per second based on the equation of the universal equation of the wave that is saying V is equal to F times lambda. We can find the frequency as V over lambda, and this will be 346 meters per second over 7.2 meters, and then the results will be 1/2, which is equal to hertz, and 346 divided by 7.2 is equal to frequency being 48.1 hertz. Again, always when you are writing a number, think about what does that number means? What is the meaning of that number? So what do you see in this open air is that the wavelength of the this particular sound, so from maximum to another consecutive maximum, is 7.2 meters, and we see this repeated 48.1 times in 1 second. Do you have any questions now?